this dream come true without success. But now, new science reveals strange paths that may finally answer the question, is time travel possible? And if so, how will we do it? Space, time, life itself. The secrets of the cosmos lie through the wormhole. In a way, every man, woman, and child on this earth is a time traveler. Like it or not, we're all being shot relentlessly forward, making the journey from birth to death, and there's no going back. And there is no way of looking into the future. Or is there? What if we could travel back to witness events in the distant past? Or journey into the far future, see our destiny? Just think what we might learn if we could watch history unfold right before our eyes. Or what we could change in our own lives if we had the chance. For many, life's greatest sorrow is losing a loved one. The time I spent with my grandmother when I was a child helped make me the man I am today. I often wish I could see my grandmother again, or go back in time and show her who I am and what I've become as an adult. Seems like an impossible dream. But is it? Can science find a way to tear down the walls between now and then? Is time travel possible? To find the answer, we must first understand the nature of time. And that's a lot harder than it sounds. Steve Jeffords is an atomic scientist and master timekeeper.
We all, I think, have some innate feeling that we understand time. It flows past us. Time goes on. We get older. Things that happened yesterday are not happening today, etc. But I don't think that any of us, whether we're physicists who study time or just somebody who lives his life, really truly understands time.
Steve works at the National Institute of Standards and Technology in Boulder, Colorado. It's one of 6 labs around the world that calculate coordinated universal time, the official world time. This table full of lasers is the NIST F1 cesium fountain atomic clock. Measuring the nuclear vibrations of atoms, this clock ticks at 9 billion times per second. That's 1/10,000,000th of a nanosecond.
This clock will measure frequency or time interval out to almost 16 digits. Why is that important? The reasons to measure time or frequency this accurately, well, there are a bunch of them. Some of them are scientific, but some of them are really practical. Systems like the Global Positioning System, the GPS system, it's fundamentally a timekeeping system. And so what we do is we put atomic clocks on satellites, make sure they're all synchronized, and now I stand on the surface of the Earth with my GPS receiver, and it gets time signals from each of these satellites, and it just measures the arrival times. And so if the signal from that satellite arrives 5 nanoseconds before the signal from that satellite, it says, oh, I must be 5 feet further from that satellite than that satellite. So it does that with 4 satellites, and it computes your X and Y position and your altitude, and now you've got your position from time. And the fact that this works at all is just remarkable, but it absolutely depends on having time at the nanosecond level. Because if you don't have time at the nanosecond level, then you can't tell which satellite you're closer to.
Precision timekeeping like this makes our high-tech, computer-driven lifestyles possible. But as our timekeeping systems become ever more accurate, we find that time does not flow the way we think it does. Time is not universal. The strange truth is that time is personal. What time is it? Well, that depends on where you are and what the ground beneath your feet is doing.
Anytime you put a clock in a gravitational field, as you get closer to the strong part of the gravitational field, the clock slows down. What ends up happening is that the Earth is not rigid. And the Earth is sort of a squishy, firm ball of jello or something. And every day when the tides go in and out, the Earth deforms sort of like a ball, and the earth under your foot goes up and down by a foot, more or less. Depends on where on the earth you are. So if I pick this clock up and move it up by a foot, it's further from the center of the earth. The gravitational force goes down a little bit, and the clock ticks a little bit faster. So now if you have a clock which is accurate to 17 digits, all of a sudden, every day, you can see the rate of the clock speed up and slow down and speed up and slow down relative to what it should be, because the Earth is squishing by this kind of 1 foot level.
Humans don't perceive these minuscule time differences, but our very fastest clocks can cut a second into a quadrillion pieces. And at that scale, we see that time differs from place to place. Time and space are tightly locked together.
Quickly, we're getting to the point where we're going to have to start thinking about space-time together rather than space and time, which is, is a cool thing, cool place to be, right?
Gravity slows time, and this is the key to one form of time travel. When you leave a gravity field such as the Earth's surface, time moves at a different rate for you than for your friends on Earth. The time difference is greatest when you move at high speed. This means that time travelers walk among us. These are their time machines. Cosmonaut Sergei Krikalev is the world's greatest time traveler. Krikalev has spent 803 days moving at 17,000 miles per hour. He traveled fast outside the Earth's gravity, so time moved more slowly for him than for us. Because time passed at different rates, he has traveled into the future, a 48th of a second into the future. A 48th of a second may not sound like much, but stick more power behind him and make him go faster near light speed, about 670 million miles per hour, and things get strange. If he travels for a year, he'll come back and find out that while he has aged 12 months, Earth is 10 years older. Here is another time machine, and it speeds things up even faster than our rocket ships. It's Europe's Large Hadron Collider, or LHC, the world's biggest and baddest particle accelerator. Steve Nunn is a professor of physics at MIT. Using the LHC, Nunn and thousands of other scientists turned pieces of atoms into time travelers. They take protons, accelerate them to nearly the speed of light, then smash them together. The subatomic particles that come out of the explosions only live for about a billionth of a second. But in the LHC, that billionth of a second is stretched out relative to our time.
The LHC here at CERN is like a time machine because of a funny feature of physics. Velocity is not what you think it is. Velocity at normal speeds is normal, but at very, very high speeds, velocity has a maximum limit. So the protons in the ring are traveling near the speed of light, and they can't go faster. What happens instead is that their clocks start moving slower. Their ticks are longer than our ticks. So in some sense, the protons that are going around the ring, their clocks are moving slower than our clocks, so they're like time travelers relative to us.
The time-traveling protons at CERN show us that we too can travel far forward in time. Decades from now, spaceships traveling near the speed of light could fly into the stars on a 10-year mission. For the people on board, it would be 10 years. On Earth, 1,000 years would pass. The astronauts would return to a far different future world. Time travel into the future is possible. But is it a one-way trip? Can we make our dream of time travel backwards and forwards come true? With the right technology, time-traveling spaceships could take us into the future. But can we go against the arrow of time and journey into the past? Well, it may not be as hard as it sounds. I mean, after all, the past is all around us. Consider this. The speed of light is 186,000 miles per second. Now, that's awfully fast. But when a piece of light travels from here to there, it takes time. And that means that everywhere you look, you're looking back in time. It takes 1/1000th of a second for light to travel 1 foot. So you see the person you're sitting next to 1/1000th of a second in the past. The light from the sun is 8 minutes old when we see it. And the deeper we gaze into the sky, the farther we see back in time. Satellites have photographed the edge of the universe, 13.7 billion light years away. That's 13.7 billion years back in time. We always look into the past, but it goes even deeper than that. According to Einstein, time is just like space. Since every bit of space exists here right now, that means that every bit of time exists right here, right now, too. Sean Carroll is a physicist at the California Institute of Technology.
Physicists tend to be eternalists. They think that the whole universe, the whole four-dimensional space-time in which we live, is equally real. We exist at different moments in this space-time continuum, and we feel different things at different moments of time. But it's not that the future is becoming real as time goes on. It's just that the future exists just as much as the past or the present. We're discovering what happens in the future as time goes on. But it's not becoming any more real, and the past is becoming real. So we think that in principle, the past and the future exist just as much as the present.
The whole of time is all around us. But can we jump from the present to the past? In the early years of the 20th century, a young patent clerk named Albert Einstein gave us a possible way back. Riding to work on a streetcar, the barely 20-year-old Einstein looked up at a clock tower, and suddenly it all clicked. Einstein realized that time is relative to where you are and how fast you're moving. Time is the fourth dimension, bound tightly together with length, width, and depth, the dimensions of space. A few years later, Einstein used his ideas about gravity's effect on space and time to create a mathematical map of the cosmos. He proved that the fabric of space and time is curved. If the universe is curved, there might be ways to build bridges across it, or create loops inside of it, loops that will allow time travel. That was the conclusion reached in 1949 by the mathematical genius Kurt Gödel. Gödel was a close friend of Einstein's, and he decided to see if the great man's equations permitted time travel. He found that they did. If the universe rotates on its axis and you somehow remain perfectly still,